Alright, this is our final project for 530.241. It is a motor velocity control circuit controlled by potentiometer. It also has these quality control circuits to let us know what's going on in the circuit. In this video we're going to explain a little bit about our circuit and how it works. So our main goal of this project is to control this DC motor. And the specifications we were given were we want the motor to operate between positive 2.5 and negative 2.5 volts, which should correspond to positive 5,000 and negative 5,000 RPM. Also, we needed to have these first two quality control circuits. Those were required, and this one is an extra credit one. I'll explain a little bit more about this later and the objectives of those. Alright, so this is part of our circuit diagram. We'll be referring to our circuit diagrams for parts of the video. First, we had to figure out how to get positive and negative 2.5 volts. We accomplished that by working in between the positive 18 and negative 18 that were specified in the project. And to get the positive and negative 2.5, we made use of Zener diodes. These Zener diodes, when you run a current of 20 milliamps through them, they provide a voltage drop of 2.5 volts. So we calculated what resistance we needed to produce a current of 20 milliamps from 18 volts, and we put that in. So that essentially means that at this node in the circuit it'll be positive 2.5. So we took the 2.5 from that and then basically ran it in reverse to get the negative 2.5. And these positive 2.5 and negative 2.5 we connected to a potentiometer, which we use to control our circuit. And basically when the potentiometer is turned, you can create any V command that you want in between positive and negative 2.5. So this is the corresponding part of that circuit diagram. Here's the positive 18 volts, runs through the resistors, runs through the Zener diode, and then to ground. And right here is the positive 2.5 volts, which we ran to the potentiometer. Likewise, from ground it runs through the Zener diode, through the resistors to negative 18 volts, and right here is the negative 18 volts, which went to the potentiometer. And our V command is the middle terminal of the potentiometer, and it varies in between the two. Alright, so the next part of our circuit takes the V command that we produce through the potentiometer, and it runs it through what is called a differential amplifier with resistor values R1 and R2. Now these resistor values have a ratio of 3.57. This is a theoretical gain that we want, that we calculated from different components in the system, from the constants of the different components, such as the motor and the tachometer. And this differential amplifier produces VACMD, or V amplified command, which then runs into our current amplifier. And this current amplifier takes the input voltage and creates a current proportional to that voltage, and that current powers the motor. Now the point of this is of the differential amplifier, it takes the difference between V command and V tach. So essentially when there's a difference here, through these two components, a current will be provided to the motor to adjust the speed of the motor to whatever we want it to through V command. Alright, so now we're focusing on the differential amplifier that we created. This is a regular LF411 regular op amp, and the inputs V command is this entire rail along here. So we ran resistors in the correct orientation from V command, and V tach from the tachometer is along this rail along here. So that's this resistor coming in from here. So this is the differential amplifier. The output here, this runs to the current amplifier, which is fitted on this circuit board. And this is the 2 ohm resistor that you saw in our circuit diagram. And this provides the current to our motor, which is hooked up like this. The positive terminal of the motor and the negative terminal of the motor, like that. The V tach comes from the tachometer. This is the tachometer on the motor, this back part, and the voltage of the tachometer essentially tells you how fast the motor is actually going. So most of the operations that we do in our circuit are comparing V command, which comes from the potentiometer up here, and VTach, which is what's actually coming out of the motor. Alright, so what we just showed you was the main part of our project, which was simply the motor velocity control. Now we're going to go into the quality control circuits with the LEDs. So this right now is our first quality control objective, which was to light a green LED when the motor velocity is positive and light a red LED when the motor velocity is negative. So this is the positive velocity green LED circuit. This boxed portion is a comparator. The part number is an LM311, and I'm going to explain how a comparator works once, and then we won't explain it for the rest of the video. But what the comparator does, it compares two voltages. Right here we have VTach and ground. So it will take the difference between these two inputs, which we'll call VID, and this dot right here means that it's an inverted signal. So when the VID is less than 0, that actually means the output right here will be high, which means this is a transistor, which means the transistor will be powered and it'll be on, and that means this voltage right here will be low, about 0 volts, and because this voltage is low, that means current flows through like this, and because current is flowing through, the LED will be on. So we essentially configure the inputs however we want them for the LEDs to be on or off. So this is the circuit with the green LED. It will be on when VTach is greater than 0. And this is the red LED circuit, and the LED will be on when VTach is less than 0. Also, we're going to explain right now how we calculated this R value. So if too much current is run through these LEDs, they'll essentially explode. We actually exploded one while we were constructing the circuit. So we chose a current that we wanted of about 20 milliamps, and we know that from part specs that these LEDs have a forward bias voltage of 2.2 volts. So we simply used V equals IR to obtain a resistor value of 790. It would have been hard to make a 790, or tedious to, so we just used a voltage of 820, which actually produces a current less than 20 milliamps, but you know, less is better in this case, so we went with the 820. Alright, so we're going to show you our first quality control circuit right now. Right now our motor velocity is positive, so the green LED is lit, and you can see how the pins are connected here. You would have to look at a spec sheet to see what the actual pins mean according to the with the op amp, but right now the motor velocity is positive, so the green LED is lit, and we turn to negative and the red LED lights up. Simple.